here with one more flipped classroom video. 3 tips before we start. You can always speed up or slow down this playback speed if that helps you get through the video. Second, you can pause the video at any time and catch up on your notes. Last, you can turn on the captions and watch my words go by on the bottom of your screen. Today's lesson is about what's called the Fundamental Theorem of Calculus. And so what we're going to do is we're going to formalize what we've done in the last few lessons where we've been calculating areas. I'm going to introduce some notation for you, and then we're going to do a bunch of calculations. But first I want to set the stage. We've been talking about finding the area under a curve. So far, I've used geometrical examples where we could check our work just by using geometry to calculate the areas that we could also find by taking integrals. But now I want to show you one where that's not so easy to do. Okay, so for example, I have this particular function. It could be any function that creates this upward curve, and I want to find the area between A and B on this curve. And so that's going to be, we know, that's the integral from A to B of f of x. And we could take the integral, do the integration, and we could get that area. Sweet. Now let's take a look at what it might look in a geometric sense. We have a curve. It's kind of hard to get that, but one of the techniques that we would do is we divide this curve up into rectangles. Okay? And so what I would have here is I have 2 rectangles that I can then calculate the area of and add them up. And that's going to give me an approximation, but it's going to leave out these weird shaped regions. So, what could I do to make that better? Let's erase these rectangles. Think about that for a minute. What could you do that would make that estimate better? Think about more rectangles. What if we did something like this? We did one rectangle there, and then a second one there, and then a third one there, and you can kind of see, just draw this quickly here, where now my rectangles are, I have less wasted space, let's put it that way. So the area of all of these rectangles is going to be much, much closer to the actual area under that curve. So what we do, what integration is going to do for us is take the number of rectangles and basically run that up to infinity. Because the smaller the rectangles are, the less you lose. So when the rectangles go to infinity, then we have the full area under the curve. And that's what integration does. I have another video that approaches this with much more detail, and we'll take a look. I think I might assign it in our class, or I'll just give it a link below if you're interested, because it's quite an interesting treatment. Okay, here it is. Doesn't look like much, but this is used for a lot. This is kind of pulling together a whole lot of what we did, and it's going to give us a foundation to finish out this unit. So check this out. If f, that's little f, is a continuous function, so there's no gaps, there's no undefined sections or anything like that, continuous function on the interval of a, or of x is greater than or equal to b and less than or x is greater than or equal to a but less than or equal to b, then, and now here's some new notation, capital F is defined as the antiderivative of little f. Okay, so we haven't talked about that yet. You might have noticed it in our textbook. It is a pretty standard notation for antiderivatives. I tend to skip over it and go right to integrals, because antiderivatives is like talking about anti-multiplication instead of just saying division. So anyway, if little f is a continuous function on the interval between a and b, and capital F is antiderivative of little x on that same interval, x between a and b, then here is what's true. Now, I've got 3 things equal. This first thing is just stating what this is. So the integral of f of x from a to b is the antiderivative of x, or is the capital F of x, that's the antiderivative, which is the integral. So we're just saying antiderivative integral. And with this function, the way we specify the interval is by doing square brackets and doing a to b. Means the same thing, which is part of why I don't spend too much time on this notation, just because it's a little confusing. Okay, anyway, integral, antiderivative, same thing. What this is, if you're evaluating it and getting a number out of it, like an area under a curve, you subtract the integral of b, actually you subtract the integral of a from the integral of b. And so that was when we would take on our graphical examples, we would take the furthest right one and we'd subtract the next one back to the left of that to get the area. In other words, if I have a curve like this, and here's my a, and here's my b, I'm subtracting integral of a from integral of b. Because if I just did b from 0, I would get this whole area, but I need to get rid of this part because really I'm only interested in that shaded area. So I know that was a little bit convoluted to explain what's going on here, and truth, you're just going to go down the road. You're just going to remember. And the trick is you want to take the bigger one, the further right one, and subtract the one that's to the left from that one. Okay? Okay, we're going to do a bunch of examples. And I want to warn you, for my IB students out there, this is a paper 1 problem. In fact, all the problems in this lesson are going to be paper 1 problems. So my hope is that we're not going to bury you in complex integration problems so that we can get you to focus on what we're doing with the integration. Okay, so all these paper 1 examples. For those of you who are not familiar with the IB, it just means that these you should be able to do these without a calculator. You might be prompted by your teacher to do just that. Okay, so here we go. Integral from 0 to 3 of x minus 2 dx. So there's our function. We're integrating over 0 to 3. Going from the last board, from the Fundamental Theorem of Calculus, we know that this is equal to the antiderivative over the same interval. So I'm just throwing that notation in, is the square brackets denote the interval, and now I'm writing big F of x minus 2. Okay? And so the value of this integration is going to be the antiderivative of 3 minus the antiderivative of 0. And we know that that's the integral and that's the integral. So I've set up the context. Now let's do the problem. Okay, let me walk you through this. So I took this, I found this integral here. So I just integrated x minus 2 dx, and that ends up giving us x squared over 2 minus 2x. Notice I don't put my constant on there because I'm doing definite integration now. So now I'm doing this part here. I need to do big F of 3 minus big F of 0. So here's my plug-in step for that using my integrated function. I've got that minus that. You want to remember your big brackets. Now this should be looking familiar to you because we've done this in the context of the geometric examples we did in the last lesson or 2 lessons ago. When I evaluate this out, I get 2.5. So that is the value of the integration from 0 to 3 of x minus 2 dx. Okay? We're just contextualizing it in this big line which expresses the fundamental theorem of calculus. Okay, here is that same problem taken from a graphical approach. So here's our integral. Okay, so that's where we started with on the last board. But instead of using the fundamental theorem of calculus to evaluate this integral, I'm going to jump back to geometry. Again, this is the context of what that problem is doing for us. So we are going from 0, x is 0, that's right here on the y-axis, to x equals 3, like that. And then we want the area under that curve. So when the curve is below the x-axis, that area is actually above the curve. It's between the curve and the x-axis, but we still call it below the curve. So that's this area, and if you remember from the last board, that area is negative. In fact, let's take a look at the calculation. This is a straightforward triangle, 1/2 times base times height. So the area for that block is -2. That confirms what we did last time. Now we're going to do the area for this block, and again, another triangle, so we have 1/2 times base times height. In this case, this is a 1-by-1 equilateral triangle, so it's 1/2 times 1 times 1, which is just 1/2. So to get the result of this integral, here it is, I've restated it again. The area equals the integral which is the area under the curve. That's just a cute way of saying area under the curve. And that's going to be 2, or 1/2 minus 2. Remember, we subtract the one that's further right. Well, we subtract the one that's further left from the one that's further right. I always mix those two things up. So we get 1/2 minus 2, which is negative 1.5, which is what we got last time. Okay, here's another one. Let's walk through that. Now we have the integral from 2 to 6 of 1 over t dt. And so as soon as you see this 1 over your variable, you're remembering that we do natural logs. So when we integrate this, that is, find the antiderivative, 1 over t is going to be the natural log. So this one is a super simple one. It's just 1 over t. There's nothing else going on here. So now we have the natural log of the absolute value of t from 2 to 6. So then that means to get this, I just have to subtract ln2 from ln6, which gives us ln3. Remember, this is a non-calculator problem, so you can't go find out what the natural log of 6 is and subtract the natural log of 2 and write some big hairy decimal there. You've got to keep it simplified. So here's that law, in case you need to remind that, is that if we have the natural log of a quotient, that can be broken out for the natural log of the numerator minus the natural log of the denominator. So we're going backwards on that rule. We had a difference here, so we ended up dividing to get our natural log of 3. Okay, we just did a natural log one, so you probably thought maybe we'd be doing one with e, and sure enough we are. So here is this one. It's the integral from 0 to 2 of 4e to the u du. So this time I'm going to make you try this yourself. We had 2 steps. We expressed it in terms of the antiderivative, which is the integral, and then we went ahead and solved it. So see how far you can take this one. So you can see here, graphically, we're going from 0 to 2. Here's on my curve, my 4 times e to the u power. I guess this would have to be the u-axis, not the y-axis. So here's my curve. I do not have a straightforward geometric way to calculate that area. I don't. I need to do an integral to do that. So the area, this arrow is pointing, is telling you that that's the integral from from 0 to 2 of 4e to the u du. And let's go ahead and put the answer to that out. That's 4e squared minus 4. Now that you've watched the video, take a moment to jot down any questions so you can bring them to our next class. Remember that you can always watch the video again to deepen your understanding. If you enjoyed the video, please click like or subscribe.